previous video, we have understand the product of nitric acid. And we have seen what are the chemical reactions that are taking place in order to produce nitric acid. And we have also seen the process flow sheet and process description. If you have missed that video, you can find it in the I button over here. Now, having said that, let's just move to the next topic of this nitric acid. And that is major engineering problem associated with this process. But before discussing major engineering problem, I would recommend you to one more time check out the last video, that is the process description and flow sheet of the production of nitric acid. And later continue with the major engineering problems, so that you can easily associate with the all problems that are faced in this production method. Now, having said that, the first topic in the major engineering problem is that the thermodynamics and kinetic consideration. As we very well know that in the production of nitric acid, we are using very complex type of the reactor, or we can say a converter, which serves different purpose at different levels. So it is very necessary to understand the equilibrium kinetics associated with this process. As you can see that this formation of NO is favored by increase in the temperature until an optimum is reached. So basically equilibrium conditions are favored when we increase the temperature in the first reaction, or that is the initiation reaction, where we combine ammonia with the air. Right? So the oxidation of the ammonia is being favored by the increment in the temperature. But this increment in the temperature favors until the optimum temperature is being reached, right? So after that optimum temperature, you will increase the temperature, but your reaction rate will be reduced. Now, this basically results from the provision of back diffusion of the NO into higher ammonium concentration region. So, if you increase temperature above this favorable, or we can say optimum temperature, right? If you increase temperature above this optimum temperature, your product, that is NO, will decompose back to the ammonium. So the reverse reaction will take place after certain temperature in the reactor. So it is very much necessary to maintain this optimum temperature in the first stage, or we can say first reaction of the oxidation of your ammonia. Now moving to the next thing, next major engineering problem is that alloying platinum with the rhodium improves the yield at given condition. So now we very well know that this platinum is very costly material. So we cannot use directly this platinum, right? As this, it will increase the fixed cost of the entire operation. So we are adding some another material that we known as the alloy. So here alloying this platinum with the rhodium material will actually improve the yield of the process. So entire yield of the, or we can say entire higher yield, can be achieved with the help of alloying platinum with rhodium. Now the rate of NO formation changes nearly correspond to the diffusional transport of ammonia molecule to the catalyst surface. So at the surface of the catalyst, more and more ammonia molecule will be absorbed and more NO will be produced. So we can say that catalysts play a very crucial role in this particular reaction. So it is always advantageous to use at more and more catalysts, right? But this catalyst is very precious, so we cannot use more and more catalyst. But instead of this, we are using platinum, which is alloyed with the rhodium, to give higher of the yield. Now, after discussing, let's just see the second type of the major engineering problem, and that is the process design modification. You can see here that most of the plant operate at the intermediate pressure, that is of your 3 to 4 atmospheric pressure, right? So most of the nitric acid production plant are operated at the higher pressure, that is 3 to 4, or we can say moderate pressure of 3 to 4 atmosphere, or even at the very higher pressure, right? Rather than they should be operated at the atmospheric pressure. As you can see here, rather than complete atmospheric process or with the combination of 1 atmosphere. So it is always advantageous to use 1 atmospheric pressure instead of higher pressure, because to maintain such higher pressure we require additional equipments, and it ultimately increases the cost of operation. There are some disadvantages of such higher pressure. As you can see that it lower the oxidation yield, right? So this higher pressure will reduce the oxidation yield in your first reaction where our ammonia is oxidized in order to produce NO. Then higher catalyst loss is again a disadvantage with the high pressure operation. We are losing more of the catalyst in the high pressure operation. Then high power requirements. Of course, if we need higher pressure, then we are also need to have higher power requirement to maintain such high pressure. So these are the all disadvantage to use higher pressure, right? So this is why it is always preferred to operate our system at the atmospheric pressure. And this also concludes the major engineering problems associated with the nitric acid production method. Now let's just quickly see what are the application of this nitric acid. Well, this nitric acid is being largely used in the production of the fertilizer. It is used as a source of nitrogen for different fertilizers, right? Then this nitric acid also finds its large application in the dye industries, dye or any fiber industry, where we are using nitric acid and we mix it with the sulfuric acid in order to get mixed acid. And this mixed acid is being used for the dyes intermediates. Then next application of this HNO3 is in the explosive industry, particularly to produce TNT. Then the next application is in the plastic industry. And lastly, we use HNO3 in order to produce ammonium nitrate, which is again one type of the fertilizer. So these are the different applications of the nitric acid. Now, having said that, let's just move to the next product in the segment of the nitrogen. As you can see that the urea. So this urea is being largely used as the fertilizer and it has highest content of the nitrogen. As you can see that this urea contains around 46% of the nitrogen, right? It is easy to produce and transport in a bulk with no explosion hazard. So we can say that this urea is very safe kind of the fertilizer, right? It can be easily transported or it can be easily produced. So now let's understand the different properties of urea. As you can see here on the screen that the molecular or empirical formula for the urea is your NH2CONH2 and it has molecular weight of 60.05 gram per moles and it has melting point of 132 degrees Celsius while its boiling point is around 165 degrees Celsius. And urea is very much soluble in the water. It has a specific gravity of 1.335. So these are the all properties of the urea that can be helpful to answer MCQ type of the question of different competitive exams. Now, having said that, let's just quickly move to the manufacturing method of the urea. As you can see here that ammonium carbamate decomposition is the method that is generally used for the manufacturing of the urea. So in order to manufacture urea from ammonia, we are producing this ammonium carbamate product, right? And this process is also known as the ammonium carbamate decomposition process. So here on the screen, you can see that different raw materials that are required for the production of the urea. Well, of course, your basic raw material is ammonia and carbon dioxide that is derived from the synthesis gas, right? So now let's just see what are the quantitative requirements for this method, right? You can see here for the production of the 1 ton of urea, we are going to require around 1.15 tons of the ammonia and around 1.47 tons of the CO2. Then the power requirement for this process is 210 kilowatt hours and the cooling water required is 120 tons. The steam requirement is around 1.8 tons. And lastly, the plant capacity of 100 to 1500 per tons per day can be achieved with this method. So here on the screen, you can see that this is the granules of the urea and this is the prilled urea, right? So basically this prilled urea is more preferred for the fertilizer purpose instead of this granule urea, right? This both type of the urea is being produced with the same method. But we always want to produce this prilled type of the urea and that we will see when we understand the process description of this process. Now, having said that, let's just quickly see what are the chemical reactions that are taking place in order to produce urea. As there is two main chemical reactions that are associated with the production of the urea. In the very first reaction, you can see here that carbon dioxide is being reacted with the 2 mole of the ammonia in order to produce this compound, which is known as the ammonium carbamate. Let me just take a pen here. You can see that this ammonium carbamate has NH4 attached with the COO, right? And on the another side, it has ammonia group as this. So this ammonium carbamate is not your urea, and we do not want to produce this ammonium carbamate. So we further react this ammonium carbamate and decompose it in order to produce a urea. So you can see here that the second reaction in which we are reacting this ammonium carbamate and decompose it to the give urea and water. So you can see here that one oxygen from here and two hydrogen from this particular NH4 are being consumed in order to produce water molecule, right? So again, this particular reaction is endothermic reaction. As you can see here that the first reaction, which is your reaction between ammonia and carbon dioxide, is exothermic with the heat of reaction around minus 37.4 kilocalories. While the second reaction of the decomposition of the urea, of the decomposition of ammonia, is endothermic reaction, which means we have to apply heat in order to carry out the reaction. And it is having heat of reaction as 6.3 kilocalories. Now there is undesired side reaction is as well, which ultimately produces butyrate. And this butyrate is our byproduct which we do not want to produce. And this butyrate is nothing but your granule forms of the urea. But we always want to produce urea in the prill form as it is more efficient. So after understanding this chemical reaction, now let's just quickly see the process flow sheet, right? So here in this image or this animation, you can see the complete flow sheet of the production of urea. It starts with this particular point where we compressed our CO2 and ammonia, and both the gases are mixed together and directly sent to the reactor. Or this particular reactor is being well designed and it is known as the autoclave, inside which we achieve higher temperature and higher pressure as 185 degrees Celsius and pressure of around 180 atmospheres. So as we very well know that the first reaction of the production of ammonium carbamate is very much exothermic reaction. So we always have to supply cold water, or we can say chilled water, in order to remove exothermicity of the reaction. So in the first autoclave, we will convert our reactant into the ammonium carbamate. So here you can see that now this green section is your ammonium carbamate. Now in this autoclave, around 35 to 37% of the conversion is being achieved. That is your 37 to 35% of urea is being produced in this autoclave. So the product contains urea, this ammonium carbamate, unconverted carbon dioxide and unconverted ammonia, and some amount of the water as well. All the product coming out of the autoclave is directly sent to the flash evaporator, where we maintain around load pressure of the 27 atmosphere and temperature of 140 degrees Celsius. And we try to concentrate our urea and decompose ammonium carbamate. So here you can see that under the application of the lower pressure, that is a 27 atmosphere, all the ammonium carbamate can be decomposed to give urea. And this product is further sent to the flash drum evaporator, which operates at the under vacuum. And here we will get our ultimate aqueous solution of the urea. So you can see here around 80% of the aqueous solution urea can be achieved in this flash drum, while the remaining unconverted product is directly recycled back to the autoclave. So here in this image you can see that first evaporator product coming out of the evaporator is again sent back to the autoclave, and the bottom product is then further heated and passed through the second flash drum, which operates at the 1 atmosphere, where we produce aqueous solution of the urea, and remaining gases are again recycled back, right? So which contains ammonia and unconverted carbon dioxide. Now the product coming out of this flash drum is sent to the vacuum evaporation, where we achieve higher concentration of the urea. That is, your urea That is, the urea is being concentrated from 80% aqueous solution to the 90% highly concentrated urea. As you can see here that the into 99% highly concentrated urea. As you can see here that 99% of the molten urea has been produced from this vacuum evaporator, which operate at the 60 centimeter of the mercury at 135 degrees Celsius. Now this molten form of the urea is sent to the preheating tower, inside which we pass cold air, right? So this cooling air convert this molten form of the urea directly into the prills, or we can say fine granules powder, that is being known as the commercial grade of the urea. So here you can see that we are passing cold air which convert this urea granules, and we make sure that we provide sufficient amount of the residence time so that we can reduce the production of the side reaction and the byproduct of the burette. With this kind of the arrangement, we can produce 99% of the urea and less than 1% of the burette is being produced. So this is the entire process flow sheet for the production of the urea. Let me just quickly revise this entire thing. So initially we have started with this compressor in which we compress our reactants, that is your carbon dioxide and ammonia, and we mix together them and send to the autoclave, inside which we achieve higher pressure of 180 atmosphere and we achieve temperature around 185 degrees Celsius. Basically in this autoclave we achieve the first reaction that we have seen in the chemical reaction, and we convert this our reactant into the ammonium carbamide. And this autoclave we achieve around 35 to 37% of the conversion into the urea, while remaining unconverted reactant and the produced ammonium carbamide are then sent to the flash evaporator, which also operate at low pressure of the 27 atmosphere. And the upper product are directly sent back to the reactor, which contains the unconverted reactant and unconverted ammonium carbamide. Then further we pass this thing through the flash drum, and lastly we operate this entire mixture, and then we pass this product stream to the flash drum where we produce 80% of aqueous solution of the urea. Then this aqueous solution of urea is passed to the evaporator which operated under vacuum. So in order to remove all the water and byproduct from this evaporator, and we ultimately get 99% of the molten urea. So we increase the concentration of the urea from 80% to the 99% with the help of this vacuum evaporator. And later this molten form of the urea is sent to the preheating tower, inside which we pass cold air so that we can convert our molten form of the urea directly into the fine granules or powders. And ultimately we produce commercial grade of the urea at the end of the process. Now, having said that, let's just quickly see the process description of this process. As you can see here that ammonia and compressed CO2 are added at the high pressure autoclave, as we have understand in the flow sheet, to produce urea. Since this reaction is very much highly exothermic, hence water is being supplied to the outer jacket. Then after average residence time of 1.5 to the 2 hours is being given in order to achieve 35 to 37% of the conversion. And ammonium carbamide and H2O and unreacted carbon dioxide and ammonia is being produced. Now these products are sent to the flash evaporator which operate at the low pressure of 27 atmosphere, where we remove unconverted reactants. Then later an aqueous solution of ammonium carbamide and urea is passed through the flash drum which operate at 1 atmosphere in order to produce 80% concentrated solution, or we can say 80% aqueous solution of the urea. Then in the later stage this aqueous urea is sent to the vacuum evaporator to increase its concentration to 99%. And then this molten mass of the urea is sent to the preheating tower where we produces fine powder of the urea by solidifying this molten form of the urea with the cold air. So this is what all about the process description of urea. In the next video, we will understand major engineering problem associated with this process. Till then, keep watching, keep learning. Thank you.